Good evening to everyone. So we are waiting, sir. So, sir, I think sir came. Good evening, sir. So we are waiting. So,
नमस्कार। मेरी आवाज आ रही है आपको?
हाँ सर, आवाज आ रही है सर।
Oh, that's good.
Sir, I am making host you, sir. Now.
अच्छा, ये जूम पे मेरा बहुत एक्सपीरियंस है नहीं,
तो सर आपको जब होस्ट करेंगे तो सर आप शेयर करेंगे अपना स्लाइड, नो प्रॉब्लम। हाँ जी सर,
that I will do.
तो now you are sir now host sir.
ठीक है, जब भी आप बताइएगा तब मैं शुरू कर दूंगा।
So before starting sir, I want to introduce to participant about sir. So healthy good evening to all of you for session 3 of ATAL FDP program, hybrid microgrid opportunity and challenges for renewable energy resources. I am Dr. Shivam, Assistant Professor of Electrical Engineering Department, co-coordinator of ATAL FDP. Heartily welcome Chief Guest of the Day, Professor Asheesh Kumar Singh, Department of Electrical Engineering, Motilal Nehru NIT, National Institute of Technology, Allahabad. Coordinator of the ATAL FDP, Professor Ratna Dahiya, Coordinator of School of Renewable Energy and Efficiency, Professor in Electrical Engineering Department, NIT Kurukshetra, and the faculty members and participants of the event. The primary objectives of the ATAL FDP is to provide a national forum to the faculty and research scholar to share the basic knowledge with and objectives of understanding the concepts, aspects of penetration of renewable energy sources, electrical vehicles, and with hybrid microgrid operation. Now, I would like to address of today's session a speaker, Professor Asheesh Kumar Singh. Dr. Asheesh Kumar Singh is a professor in Department of Electrical Engineering, Motilal Nehru, National Institute of Technology, Allahabad. He did PhD from IIT Roorkee, Master in Control System, Department of Electrical Engineering from NIT Kurukshetra, BE in Electrical Engineering from Hardcore Butler Technical University, Kanpur. His area of research are power system, power quality, e-mobility, renewable energy integration, microgrids, and a smart grid. He has guided more than decade PhD degree students and more than 50 MTech students for their master thesis. Currently, many doctoral students are working with him for their PhD degree. He has published many international and national papers. If you are interested, you may visit on Google Scholar link. Now, welcome, sir, to the session. Thank you.
Thank you, Dr. Shivam. Thank you for inviting. It is always a pleasure to be virtually or physically at NIT Kurukshetra because that electrical engineering department, I have stayed there for my MTech, and it is my pleasure that you are inviting me for this lecture. I'm thankful to the faculty members of the electrical engineering department and NIT Kurukshetra in large that they have. I still feel their tremendous contribution in my career. I'm really obliged for that. So let's come back to the topic. Just a minute. Yeah. Is it visible?
Yes, sir. It is visible. It is visible, sir. Now.
Okay. Okay. Something is wrong here. Okay. My screen is visible, Shivam sir?
Yes, sir. It is visible, sir.
Let me make it full screen.
It's okay, sir.
Okay, good. So, good evening to all of you that we are here in this ATAL sponsored hybrid mode faculty development program on hybrid microgrid titled Opportunities and Challenges for Renewable Energy Resources, organized by Electrical Engineering Department of MNNIT Kurukshetra in the during this period of December 2023. I've been assigned this responsibility to deliver on microgrid concept, key challenges and issues. So, what we will discuss today, that is, we will first try to discuss some concept of the energy, basically, which is the part of renewable energy. Also, we will try to discuss those things. Then, especially electricity, we will talk the under this energy concept, and then we will try to move this renewable energy. Then we will try to discuss this distributed generation and distributed energy resources, some definitions and classifications, their overview. Then we will try to touch some ancillary services, some basic details about them. Then we will try to come this basic theme of the lecture, that is microgrid, its concept, types, advantages and limitations, backgrounds, some very foundational research which was done in some initially it was which was performed in some countries with some dedicated objectives. Then we will try to get some objectives, classifications, architectures, control strategies. We will simply try to introduce a few basics, though it is not the part of in the scope of this lecture. And then energy management systems of microgrid, operation and control, drivers of microgrid development, deployment of microgrid at different locations globally, then some future trends, challenges, and open questions. So in this way, we will move through this lecture. We will try to discuss some very basic things, right from the very basic things to some difficult questions, and what are the future challenges which are yet to be addressed to make this technology popular, right? So we will try to move in a very basic, simple, you can ask those questions. I will definitely, you may ask during the session also, and if you have patience, you can ask them in the last also, okay? So, initially, we will start right from the thing of energy. That energy is always, it is considered as a very basic question, very basic and reliable source for doing any job, right? And being an electrical engineer, we are typically concerned about the electricity, right? So why energy is required? Energy is basically required as one of the foremost crucial measure related to the economic growth of the nation and the human advancement, technically, socially also. So for all these aspects, we need energy. And among these, the electricity is popular because being this clean, efficient, affordable, and reliable energy services, right? And it is treated presently as an essential service for global prosperity. Power generation and distribution has always been key feature towards the development of modern society. Being the community member of this power engineers, we are concerned due to the increasing energy demand globally due to different reasons. It may be due to the urbanization of the population, or it may be to the advancement of the technologies. It may be due to the continuously increasing industrialization in different part of the globe. And second concept is diminishing of primary energy availability. Third is the infrastructure, which is almost more than 100-year-old now, because generation and this electricity business is more than 100 years old, right? So this traditional and aged electrical transmission and distribution network, that is also a big concern, as it needs some maintenance or some renovation or some expansion in different parts. That's why this is a big concern. Shivam, where is the control for this?
Yes, sir.
Yeah, there is some this restriction for bandwidth actually, right? So I will, when I will this section will improve, I will try to open it again, right? So this traditional, I will come back to the topic, this traditional electric power grid that has been designed to accommodate the traditional energy distribution system, which makes it difficult to keep on changing or accommodating the different changes for this power and energy generation. This electric grid, which is in our service, it faces many challenges related to this future development towards improved power generation and distribution systems, right? And it is continuously trying to accommodate the aspect of distribution automation also, just to increase the reliability of the system, so that the customer who is paying for the electricity and who is always in need of electricity shall get it continuously. So identifying those challenges and developing necessary strategies to face these challenges or reply those questions continuously, this is critical towards the growth of the system. The growth of world population, it has continuously necessitated this dramatic increase in the energy demand globally, as the population who is using electricity for its different uses throughout the day, that is also increasing. Number of equipment, that is also multiplying day by day. So in this context, the consumption of electricity is increasing, and expected this use, it is expected that this amount of energy use or electricity use will also be increased in future. An assessment of 2016, it was made by this International Energy Authority, that was International Energy Agency, basically IEA. They forecasted that there is going to be a 30% increase in world energy demand by 2040. Yes, it is also expected that more than 50% population who is going to use electricity, that is going to be increased. But here, this percentage of consumption of electricity is not going to be in proportional, because it is expected that the improvement in the technology of the power consumption, in this way, by the improved technology, this power and consumption is also going to this is okay. This screen was gone actually. So this is also going to be a trend, but not in that proportion of the population increment, because as I told you that this increased equipment efficiency is going to be a reason for that. So what happens? Presently, this most of this demand of electricity is being used or fulfilled by fossil fuels, mainly by coals presently. At least this trend for renewable energy has started, but still not has been a successful substitute for fulfillment of the complete load. So what is happening right now? This energy conversion process right now is burning of fossil fuel, then releasing heat energy, and definitely this conversion into electricity. So this conversion of energy, transformation of energy, it is going through several stages, and every stage has its limited efficiency. So the overall conversion efficiency for the system is not that good. And there is also a threat that this conversion process causes increased greenhouse gas emissions, which is a threat for the climate change, right? And which is a threat for the global warming issues. And there is a question mark of, there's a big question mark on the temperature increase of the globe by that 1.5 or 2 degrees centigrade, that crucial number. So that is definitely a very crucial number for temperature increment of the globe by this impact of this greenhouse gas emissions, by this climate change, and that is a threat. And this is the motivation for use of renewable energy generation or the technology of microgrid. So these renewable resources, they are the solution for these threats or to overcome these threats, right? And these are also implemented as a goal of United Nations Sustainable Development. They call it Goal 7 basically, that is affordable and clean energy, right? And there are several different agreement also, Paris Agreement, Kyoto Protocol, etc. They are presently or in the past have been implemented by the global leadership to come on to make a consensus on this particular issue. So what is renewable energy? A very simple definition of renewable energy can be considered as, it is defined as energy produced from natural processes which are inexhaustible, right? The RERs offer a solution to the challenges. Renewable energy resources, we are referring them as RERs. They offer solution to the rising electricity demand because they do not provide any global warming threat due to the emission of these greenhouse gases, GHGs, right? This particular solution of electricity from RERs, that is quite environmentally sustainable because they are non-conventional resource of the power, electricity as we consume them. And the third is, that is the most important and most useful also, that it has the ability to provide power to even the most underprivileged people living in the remotest areas where traditional power is still not available. And I think this is the most precious service which these renewable resources are doing to the humanity. And that's make them more useful, more important. So these renewable resources, they are being classified in the literature, which is available in abundance. They have been classified as hydropower, solar power, marine, bioenergy, geothermal, wind energy, right? I have taken it from a recent paper of 2022, but this all is available in even books also. So, but this classification, this further goes from hydropower to renewable hydropower, mixed hydro, solar energy, marine. This goes in different classifications. You can refer this paper of 2022 for further reading in that direction, right? If you have any question, we can discuss in the last. So these renewable energy resources can be classified by dispatchability and being the non-dispatchable sources. What is dispatchability? Dispatchability is a characteristic which is sources ability to adjust the power output. And that requirement comes from the power system's requirement. Shivam-ji, am I audible?
Yes, sir. It is audible, sir.
This internet connection is showing unstable. Actually, that's why I'm just asking in between. Okay.
Yes, it is going smoothly, sir. No problem.
Okay. So this dispatchability is a requirement, which is a basic requirement for making any resource of electricity as a useful resource, right? So these renewable resources, they are referred as non-dispatchable resources because their generation is not fixed, right? And we refer them as an intermittent source, depending upon the availability of the natural resource for that. As it is clear in the case of solar, it is the sun who is responsible, and in case of wind turbine, it is the speed of the wind, right? But recently, this addition of successful integration of storage with a cheaper cost and with the in this introduction of electronic converters, this storage integration has made these renewable resources as a dispatchable source. This combination is dispatchable. Okay. But there is a question that in some literature, this large hydropower is not considered as renewable resources due to extensive environmental impacts and emissions, which are greenhouse gas emissions, which are associated with it. This is a study which was made in 2000, which was published in 2004, and definitely it was made before that. It was done in a different power dams of Brazil, right? And they have done some experimental measurements, determined that the greenhouse gas emissions, which were formed through this bubbles formed on the lake bottom by decomposition organic matter, and they found that the greenhouse gas emissions, mainly nitrogen, CO2, and methane, CH4, they were produced underwater through biomass decomposition by bacteria, and they were at par with the generation by some thermal power plant. This was established through some experimental measurements, right? And that was the reason which declines for this large hydropower to be treated as this renewable resource. So this means some meteorological factors are responsible for this intermittence, uncertainty, or randomness of renewable resources. But as I told you, that this integration of storage with power electronic control has made it in this dispatchable. So here comes the term distributed energy resources. And this distributed energy resources are distributed generation resources. They refer on-site generation. We are aware with that, right? And this on-site generation means it includes the storage also, right? So these examples are renewable resource is a part of or a subset of this DER. We are reading a new term, that is DER or DG. So RER is a subset of this DER. It also includes micro-conventional generators, micro-turbines, energy storage systems in large, fuel cells, reciprocating engines, Stirling engines, photovoltaic systems, especially rooftop solar, combined heat power CHP or cogeneration or trigeneration, you can say. Some different literatures refer it with some different name every time. Small wind power systems, hybrid power systems, it may be a combination of solar and wind also, and it may include some other sources also, which is a fashion nowadays for mixed or hybrid power systems, or a combination of some or few or all of the above, right? So this makes a hybrid power system. And the purpose of this DER or DG is to provide an alternative of existing power system or enhancing the capacity of the existing power system. This capacity of enhancement in the power system capacity, this has several advantages, and we will study those advantages in later slides. So it clearly says that whatever the intermittency is, it is overcome by either inclusion of energy storage systems, or you may also provide this micro conventional generators, which are used as a continuous source of electricity at some place, right? So this micro conventional generator is a distributed generation or DER, but it is not renewable energy resource, right? So this is the difference which you will have to understand why these RERs are a set of DG. They are not at par with that. So these distributed energy resources, they cover a wide range of technology and services, and they deliver value across different parts of this supply chain of electricity. They may be renewable resources such as solar PVs, energy storage. In new technologies, they are also considered as electric vehicles and some other technologies such as air conditioners, hot water systems, pool pumps, and some smart appliances which are capable of providing services for this some attributes of the smart grid, right? They can also manage the load, given the timing of the load, etc., etc. So this particular capability of smart appliances puts it in the category of DERs. These DER systems, which serve as a storage device also, they are referred as distributed energy storage systems or DESs. The location of these DERs can be within a customer premises, which is referred as BTM, behind the meter, or it may be located in the distribution system outside the customer's premises. So these are the two different locations which are available in the literature for these DERs in the system, distribution system. Different definitions of distributed generation, they are available in the literature. If we refer right from the beginning, so this I have considered these literature right from, I've attempted to make it from 2000 or 2001. You can find it as 2001 paper of Ackerman, which was a primary paper in the area of microgrid, in distributed generation, which have a title Distributed Generation, a definition, right? So this defines the distributed generation as electric power generation source connected directly to distribution network or on customer side of meter, means BTM, right? So this particular perspective of the definition was the location. Clear? Another definition which covers the location perspective of DG definition, that is of 2000 paper, it says that it refers DG as small generating units installed close to load centers, means transmission is not required. It is the part of distribution system very close to the load. So again, the location perspective. This EPRI definition says that it has a generation capacity from few kilowatts to 50 megawatt. It is very old definition of 1998, which is not practically possible nowadays with the larger size of microgrids. This DG is available presently, right? So this was that first definition, which is on the perspective of capacity. Then comes this another definition based on the capacity, which says all generation units with a maximum capacity of 50 megawatt to 100 megawatt, which are usually connected to the distribution network and which are neither centrally planned nor dispatched. By that time, the storage was not into consideration, so that's why they are simply adding the capacity of the generation units. Then another definition says this location-based definition says that generating plants serving a customer on-site. Basically, DGs are referred as on-site generation. So this also is a location-based definition. It says that these generating plants provide support to distribution network connected to grid at distribution level voltage. Another definition says this capacity-based definition, again, it says generation of electricity by facilities that are sufficiently smaller than central generating plants, which are generating electricity at larger stations, which are based on the principles of this economy of scale, right? And so it is different from them and generating electricity at a very small level to allow interconnection at nearly any point in the power system, which is a, you may identify any point of common coupling and there you may insert it in the distribution system as a load providing or as a load supplying service. Then comes another definition of 2002 that covers the capacity and location both. It says that electric power generation or storage less than a kilowatt to tens of megawatt. They have increased the range a lot. That is not a part of large central power system. Yes, and it is located close to the load. So it defines two different perspectives. It covers two different perspectives of the distributed generation. Then another definition, which is which was given by Chambers in his book of 2001, it says that small generation units of 30 megawatt or less and located near consumer centers, right? There is a very good paper of this 2014 and 2005. These two papers, which are given in the referred in the last of the slide. At the end of the slide, you can say these are the source for these different definitions, and they are basically the point from where I motivated to get some other definitions also. So this all has been a compiled literature from different sources, and that I'm simply disseminating for your information. So this distributed generation classification, there was a paper of 2005 of Papermans. They suggest that there can be various criteria which may be used for classifying for defining DGs or classifying them, right? So they have given this classification in 5 criterions. That is point of DG interconnection, capacity, purpose of interconnection, DG technology, and ownership, right? This point of DG interconnection, which is a point of common coupling also in the distribution system, you may say, it says that it may either be connected in the distribution system if it is a very small capacity, or it may be connected if it is a high voltage network or a large capacity network, it may be connected in the transmission network also, right? There is some literature available nowadays which simply talks about the larger capacities of microgrids in thousands of megawatts also, right? Then comes the capacity. The capacity wise, they classify into this micro DG, small DG, medium DG, and large DG, right? And accordingly, they give this classification from 1 watt to 500 megawatt, right? So this is covering a very large range as per the application of various requirements and various types of customers. Then purpose of interconnection says it may be used for supply of active power also, and it may be used for provisions of ancillary services, right? And this provision of ancillary services, they are continuously being a source of motivation for different microgrid users or different sources or persons who are having their own distributed generation, right? And with their interaction with the transmission system operators and under the guidance of this distribution system operators, they are making money, or they may earn money, who users like me and you, right? They may earn money by participating in these programs of the utility companies, right? This is the latest trend in those countries where this microgrid or the clusters of microgrids are properly monitored by this distribution system operator. This DSO is still not a requirement in our country's provisions. I hope in the coming 2-3 years, they are going to be a part of the system distribution operator, and definitely this technology is going to come up in large scale in our country also. So these ancillary services, they may be on distribution network, on transmission network, they may be participation in frequency regulation, reserve requirements, reactive power, system security, power quality, voltage regulation, etc., etc. Of course, they are classified in different two classes. One is transmission network and second is on distribution network. Then comes DG technologies. They are renewable and non-renewable. This is easily classified. Then comes the ownership. As I told you, there are ownerships of three different types. One is customer owned, behind the meter. Second is independent power producers who are in the business of producing electricity or in the business of implementing these DG resources. And then utility owned. Means utility is having these distributed generation for their emergency uses or fulfilling those marginal requirements which may come time to time. So there is a report of IEA that was published in 2002, which said that why these DGs are getting popular. Basically, these DGs have become, when their integration came into a system part with the storage, that gave birth to the concept of microgrid, that we will also discuss how this concept of microgrid was started. So first we are talking about the distributed generation, its popularity, and how it paved the path for welcoming the microgrids. So in 2002, this IEA published that there are 5 major factors which are due to which this there is a significantly increased interest towards DG. And those 5 points are advancement in DG technologies, because DGs were technology was increasing, new resources were appearing, their sizes were reducing with the capacity increment. Then comes constraints on construction of new transmission lines. Because this new transmission line, laying of a new transmission line, this may be a project of duration 7 to 10 years, with a huge cost investment, right? And by implementing these distributed generations at local level for fulfillment of the local energy requirement, that may differ these investments, right? And definitely when transmission line requirements are reducing, it means the transmission losses are also decreasing. So that may be an added advantage of the distributed generation. Third point says, with DG or with adding a DG in their premises, the customer demand, they feel satisfied for their highly reliable electricity at their premises. So this adding DG has added confidence in customer towards the reliability of power system. Then electricity market liberalization was also a trend at that time, and that gave a flexibility to the different users to adopting these technologies and deciding their source of electricity. And of course, the concerns which we have discussed, which claim at different times that there is so much on stake if this temperature is going to continuously increase, and this remaining band of 1.5 degrees centigrade is passed, then there may be so many damaging effects due to this climate change. So these are the 5 reasons which have significantly increased this interest toward the distributed generation. And of course, we all know that technically it has proven, and literature is abundant literature is available about this, that this adequate combination of different digital technologies, as I told you, gave you a list and discussed that list, that a combination of these technologies may add high level of reliability and security of power system. And we will discuss which are the countries which use these distributed generation for this increased reliability of the power system. There are the countries or the set of countries who try to use these renewable, adding these renewable resources for this increment or this GHG gas emission reduction, right? So we will discuss those things in our later slides. This is different DG technologies. They have been classified into 3 different categories: non-renewable, renewable, and storage, right? And when we talk about non-renewable, they are the conventional things. They include this reciprocating engines, gas turbines, combustion turbine, micro turbine. And this renewable includes this hydro, wind, solar, geothermal, biomass, tidal, as I gave you list in the very first, in the very beginning of the lecture. And these hydros are classified in 2 different ways. Then comes the storage. Different type of storage technologies are mechanical, electrical, chemical, thermal, and electrochemical. So this we have discussed a lot. This is, we are in discussion right now. This mechanical is example is pumped hydro, CAES, flywheel. This is double layer capacitor, SMES, hydrogen electrolyzer, fuel cell, etc., etc. So these energy storage systems, which are of 5 types, we are considering here. There may be third of electrostatic also, right? So that we will consider later. So this thermal energy storage systems, what they do, they convert this thermal energy, that is heat, into electrical energy, or they may store it also in that way, and that they may release it as, they may store it as thermal energy and they may release it as electrical energy. Then comes the mechanical energy, where this mechanical energy is stored in form of kinetic and potential energy, and goes in, takes the form of electrical energy at the time of use. This hydroelectric turbines are the example of that. Pumped storage is example of that. Flywheels, they are the example of that. Then comes the chemical energy. This chemical energy conversion to electrical energy, that is a common storage systems of chemical energy. Then comes electrochemical storage systems. They convert this electrochemical energy, and the example is secondary batteries and the flow energy batteries, which are the new trend. Then comes the hybrid energy storage systems, which is a combination of different storage technologies as per their suitability. So this is a classification that we will skip because we have discussed a lot. Then we will discuss this evolution of energy storage systems. This evolution of energy storage system, if we discuss, so this is a concept which is older than the concept of the electricity. Means commercial business of electricity was done by this Edison in decade of 1880, in the early years of 1881 or 82. Before that, this fuel cell was invented in 1839. Lead acid battery was invented as the first version was available in 1859. Flywheel energy storage was developed in 1883. Nickel cadmium battery was invented in 1899. It was a rechargeable battery that has nickel and cadmium electrodes in a potassium hydroxide solution. Then 1907, this pumped hydro energy storage was installed in Switzerland first time, as per records available. They first used this pumped storage in Switzerland. Then comes this sodium sulfur battery. It was invented in 1960. It was developed by Ford Motor Companies in that decade. Then superconducting magnetic storage, SMES. It was originally introduced in the year 1969. Then 1977, this 42 borehole energy thermal energy storage was constructed in Sweden. Then compressed air energy storage, CAES. This was implemented in 1978. Initial installation was having a capacity of 290 megawatt, right? And that was a time when this 500 megawatt thermal stations were not in practice, right? So this was definitely a very huge capacity. 1982, this supercapacitor was developed in this Pinnacle Research Institute, but definitely it was developed for military applications, and this particular supercapacitor was having very low internal resistance. Then 1983, vanadium redox flow battery was developed, and this was pioneered in University of New South Wales by these team of Skyless Kajakos and co-workers. Then 1983, this polysulfide bromide flow battery. This flow battery was developed first time, and it is first reporting is available through Remick et al. In 1983. 1991, this lithium-ion battery, which is a new trend, they consider as a new trend nowadays, one of the most efficient solution and most technology advanced addition of the battery nowadays for electric vehicle application, etc. So this was released by Sony Corporation in 1991. Then 2007, the latest addition in this this chart, which you can add as paper battery. This was developed as Rensselaer Polytechnic Institute, New York, by this team of Linhart, Nalamasu, and Ajahn. So definitely there are more combinations of battery which have come or developed or under study after this. So this is, although this is a history of those things, this is not a complete history. There are some things happened in between also. They may not be commercialized that much, so they may bring into this record. Okay. So this is all about the battery. We have developed, we have discussed a lot. Now, this is all about the distributed generation, DGs, right? And this all were the examples of DGs, renewable resources and batteries, or you can say energy storage, right? So this deployment of RES-based DGs to grid, this has increased significantly in last few years. The reason is that technologically the cost of these generating sources such as solar panel or this storage cost, that has reduced a lot, right? And that is the reason this DG based generation is gaining popularity, and its presence is visible almost in every city or in almost every building in your surrounding, right? Reason is again the same thing, declining trend of cost associated. So large scale deployment in some countries, there are some government also provides some subsidy on this installations, and that is also a reason for this more increment in the capacity installation of the renewable resources. And there is a trend which was developed earlier of the utility based generation, and reason was that economy of scale. It was found that larger generation becomes. Any question? Any question?
No, sir.
Okay. So this trend of which was developed on this economy of scale, this is already gaining popularity, and this economy of scale was economy of scale was made popular in earlier years, and that's why we installed these larger generating stations. But this trend of central generation based traditional architecture grid,
Satvinder, you have to mute first. Okay, sir.
चलिए मैं बोल सकता हूँ.
हाँ, yes sir, yes sir. Go ahead sir.
जी, हम लोग बात कर रहे थे कि why this trend is increasing day by day. So this trend of distributed generation, the basic another reason is, first reason is the cost, declining cost, and second reason is the weakening trend of this central generation based traditional architecture, where large system generations, large generating stations are responsible for generation of electricity. But nowadays, this modular architecture is also increasing, which can be increased as per the requirement, and the small generating units are at service whenever and wherever they are required, right? And this is also giving rise to the concept of microgrids and then interconnected microgrids, right? This interconnected microgrid, that is also a trend nowadays, and there are so many papers on the control, application, technical analysis of these interconnected microgrids or coordinated microgrids. And third is, again, the issue is climate change. Climate change is such a havoc word, everyone is fearing that this may bring some very negative impacts, and that's why this a trend towards zero emission power system is gaining day by day. And there are different countries who have given their targets for this zero emission power systems by specific particular years. There are some specific countries in the globe who have their wind power generation more than their actual consumption of electricity, but they are not totally dependent on that wind power generation. They are exporting it to some other countries, and still they are using electricity generated by some other combinations of electricity generation. So these advantages of DGs and DRs, they may be taken as high efficiency, energy production savings, environmental protection, reduction of transmission and distribution losses. As I told you that this generation is very close to the load, then supporting local power grid by just being a part of the distribution system, and definitely when they are supporting generating stations or distribution systems, so they are contributing towards enhanced stability and reliability of the power system, right? And when these supports are available to the power system, so definitely they are a sufficient reason or deferral of the capacity investments cost on generation, transmission, and distribution. Means this local generation is ready to fulfill the need of the required load. Then, as I discussed you, they are also ready to provide or participate in the ancillary service programs offered by the different distribution companies or utilities. They are also responsible for power quality improvement. They are also responsible for providing this combined heat and power or tri-generation or co-generation, which is a need of those countries which are having some specific weather throughout the year. Then demand reduction and standby generation, they are the added advantages. So there are some ancillary services. As I told you that these ancillary services, they refer to functions that help grid operators in maintaining a reliable electricity system. That is, ancillary service is a requirement of the service provider or the utility companies, right? And through which they in this particular job, they take support of its stakeholders, who are the prosumers, who are the customers with generation capacity, right? They may, in a smart grid system, sometimes they also participate with this distribution system management or demand side management, etc. That is also a part of type of that, but auxiliary services are different from that, right? So through these auxiliary services, the utility companies, they maintain the proper flow and direction of electricity. they address imbalance between supply and demand whenever it's required and help the system recover after a power system event such as blackout or complete outage. So these additional ancillary services may be required to manage this variability and uncertainty in the power system, which is also because of this more participation or significant participation of the renewable energy penetration. And these ancillary services may be listed as synchronized regulation, contingency reserves, black start regulation, and flexibility reserves. This flexibility is a new term where research is taking place nowadays, and this is a very attractive domain, right? And if you are interested in that, you may read in this direction, and definitely this particular aspect of power system is entirely a new thing, and you will definitely feel exploring a new dimension of power system. So we are moving ahead now with integration of DERs in distribution network. There are a few other questions. That may be the optimal sizing, that may be the control required, because this integration is not directly possible sometimes. Sometimes it needs some electronic converter, sometimes it needs some different control techniques to maintain the things, and definitely when and how much they shall participate, means time of participation and amount of participation. Means when we are dealing everything with the economic perspective, so definitely in that case, when n number of sources are available for consumption of electricity, then consumer has a right to decide which electricity, means from which resource it is going to be the most cost effective at that particular moment, right? So these are the issues which are typically discussed or typically required to be answered before making their use in power system. So here comes the concept of microgrid, right? So this microgrid, we are shifting from DERs to microgrid now. The microgrid embodies these components, means DERs with electronic control, some controllable loads, some controllers, etc., which has a capacity to be operated in both the modes. Means it may be used in the grid connected mode as well as in islanded mode, right? In case of islanded mode, it is disconnected from the grid, means it is not taking electricity from the main grid, right? There is a switch at the point of common coupling in the distribution system, and using that particular switch, it is disconnected. Clear? And in that situation, it is capable of fulfilling all the load requirements of the microgrid which are existing within its geographical boundary. Means there shall be no change in the performance in terms of reliability or the fulfillment of load when it is not connected with the grid. And when it is grid connected, in that situation, it may supply or it may take electricity from the main grid. And if it is taking electricity from the main grid, in that case, it is treated as a load connected at that point of common coupling by the utility, right? And if it is fulfilling some supply requirements of the grid, in that case, it will supply power through that point of common coupling to the grid, right? So that particular role, its role in distribution system is really important for successful operation of the grid if it is connected there. So in summary, these microgrids can be referred as next generation power system, which are having distributed energy resources or DGs in it, And of course, this energy storage systems is a part of this DG and a variety of controllable loads, right? So the loads which can be controlled as per the requirement. So this is the typically defined components of a microgrid, and this communication network also plays an important role in the framework of microgrid, right? And it makes it distributed, intelligent, and integrated with the power networks when and where required, right? So this communication network plays a very important role in the control aspect of the microgrid. And in today's literature, you can find this application of microgrid in using this Internet of Things. You can find them in Industry 4.0, you can find them in smart cities, you can find them in ships, and you can find them in satellites, right? So there are some recent papers where you can find the discussion about this microgrid in satellite systems, right? So if you discuss and understand the basic definition of the microgrid, then definitely you can try to examine each and every power system. Is it a microgrid or not? You can simply make a checklist on the conditions given by these definitions of microgrid, and you can simply say, yes, this particular system is microgrid or this is not, right? So definitely we will try to examine those points also given in the basic definition. So here comes the first definition of the microgrid, which has been given by the US Department of Energy, right? And it was published in a report of 2012 from where I have collected it, right? Definitely it was given some earlier years, but it is a source, established source is this 2012 report. So this particular microgrid definition says that it is a group of interconnected loads, right? Please concentrate on the components defined by this particular definition, and they may be treated as a requirement or qualifying requirement for the microgrid for any power system. So a group of interconnected loads and DERs or DGs, definitely they include resources, conventional, non-conventional, and energy storage systems, right? Second requirement is with clearly defined electrical boundaries. Third requirement is that acts as a single controllable entity with respect to the grid to which it is connected through this point of common coupling. Fourth requirement is it can connect and disconnect from the grid, means you can use that switch. And definitely when it can be connect and disconnect, so last requirement is it must be capable of operating successfully in both the conditions, operating conditions. One is grid connected mode and second is islanded mode, right? And if we examine any given power system, what are the loads, what are the sources, what is the electrical boundary, what is the control method, and if it is found that it is fulfilling these requirements, we can declare it as a microgrid. Okay, we will examine some systems or some initial systems in some later slides. So if we discuss in detail about this particular definition, it describes three requirements. As I told you, I have highlighted them. But this definition is silent about the size of the distributed energy resources, right? And when the size of DERs is not decided, then the electrical capacity of the microgrid is also not given. Clear? Second is, it is not making any clear-cut statement about the types of technologies. Conventional, non-conventional, only renewable, with storage, without storage, no. It is silent on these two particular points. Well, there is another definition which is given by SIGRE working group, right? And we all know that there are two different communities working in that area. One is the American community and second is the European community, right? So they have given this definition. A microgrid are electricity distribution system. So at least they have defined it is not having any connection with the transmission system. It is connected through that grid only, but it is not in the transmission. It is only distribution system. Well, second point is similar to the previous one. It means it talks about it is having loads, it is having DGs, right? DGs is they are storage devices, distributed generators, or controllable loads, means smart loads, etc., as per the given definition earlier, right? It again talks about the second condition that it says that controlled in a coordinated way, means it can be operated in the grid connected mode or islanded mode. So some basic words are only different. Otherwise, you can find that these two definitions, they are almost similar. They talk about the same word, same set of words with some minor changes. Clear? So using these definitions, either that United States Energy Department definition or the SIGRE definition, you can examine any system, any given power system, and accordingly you may define or declare if this particular power system is microgrid or not. So on the basis of these definitions, this particular paper of 2006, that also comes to a conclusion that these five critical functions, they conceptualize the microgrid, right? One is nature of connection, precise energy and power balance within microgrid, energy storage, demand management, and seasonal match between generation and load, because when the season changes, the generation capacities are also different, load requirements are also different for different communities or different geographical locations, right? So these are the five critical functions, you can say, which are the decision making or critical functions for microgrid's basic concept, right? So this energy storage may be of any type, seasonal match may be between different type of resources. So these are the 5 points which we have discussed one by one. So if we say, then what is the type of the microgrid? So a particular paper of 2014, that is an elsewhere publication, that is Renewable and Sustainable Energy Reviews, it clearly defines that types of microgrids, they are given of 4 types in this particular paper, right? So it defines one as a separate islanded grid, means one small community is there, one generation is there, different very small sort of loads are there, and they are making a microgrid with a microgrid management system, right? And in this separated islanded microgrid, there may be one village, there may be one city, or some small community which may have their load requirement fulfilled by some basic renewable energy resources. It may be some hydroelectric plant, very small capacity. It may be some solar and wind power combinations with some storage, etc., etc. Then second type is low voltage customer microgrid, right? So what happens? This is a connected microgrid, very first type of microgrid, very lowest capacity microgrid, but it is grid connected, right? And example may be, it is one household that includes distributed energy resources, storage, etc., etc. within it, right? And this particular thing is connected with some similar microgrids in low voltage network. Then the third case is, it is LV network that can include many distributed energy resource units or DG units and several customers, right? And this particular thing may give rise to this connected microgrids also, if there is some consensus between them on the basis of control. If there is one distribution system operator, they may be operated under their control, and they may also contribute to the utility in some point of time of requirement, right? But this particular type, when I am talking about this LV microgrid, this is not interconnected here. They are simply units which are fulfilling their requirements. Clear? So these are some small scale DGs they may have. They may have this fuel cell, they may have some biogas based requirement, they may have some micro turbines, etc. etc. Then in fourth case, this is MV feeder microgrid, right? So this LV microgrid, that may be a combination of different LV customer microgrids also, or that may be a part of a different commercial system with some larger capacity, which is capable of fulfilling its own requirement. Then comes this medium voltage feeder microgrid, right? And this is a high voltage or medium voltage substation is also there, which is fulfilling the requirement, its requirement from the transmission system through this distribution system substation, or it may supply to the utility vice versa whenever it is their requirement, right? So these four cases, they represent four types of microgrids, right? As represented in this particular diagram. This I have taken from this paper of 2014, right? This case 4 requirement, they are the largest size microgrids, and you can say that this initial size, that may be different scales. They may say, you can say this separated island microgrid, that may be of local requirement. This case 2 requirement may be of some 10 kilowatt capacity almost, but not more than that. This case 3 may be of, which is a combination of low voltage microgrid. This may have a case of 10 to 100 kilowatt, means just larger than a multiple set of LV customer microgrid, right? And this case 4, it is the largest one, right? And this is also having the larger voltage level also, right? It is having some commercial level storage units also, and some other things which may be a part of, such as distributed management system. Then it may also have this microgrid management system. It may also be connected to energy markets for power exchange as per the requirement, and it may further connected to this high voltage substation. So this is about this types of microgrid. Then we talk about this microgrid generation and storage. We have talked a lot about this, so we will simply skip it. So microgrid helps in achieving objectives of efficient transformation of passive network into active one. Yes, it is making the consumers as a converting consumers to prosumers, right? It is achieving the objective by this thing. When they are prosumers, it means they are having this bidirectional and controlled power flow management, and definitely this is increasing the reliability of the power supply for individual customer as well as for the grid also. Definitely power quality improvements are there when it is fulfilling the additional requirement of power supply, and of course the benefit is there of clean environment, and it is definitely addressing the issues of the climate change. And as I told you earlier, this all is possible only through the better control techniques which are being developed by the different researchers, and definitely the power electronic interfaces, they are also responsible for making these controls of smaller in size and larger in capacities. So that is the requirement. That is the result of the this new development of the new technologies of the recent years. And if we talk about the advantages, the MGs, advantages of microgrids, you may say that they are offering those advantages in multiplication, which were the advantages of the distributed generation, right? So we can simply classify them as environmental, operation and investment, power quality, market. These are the advantages in addition to the ancillary services, smart grid attributes. They all can be the advantages which may be made available through the uses of or the availability of microgrids, right? And the deferral of the capacity investment, reduction in transmission and distribution losses, they all are also a part of it, because microgrids, they reduce the physical and electrical distances between the sources and load due to the presence of distributed generation, right? So we'll move ahead. If you have any question, I'm ready to take. But just because of these advantages, other than these advantages, these microgrids have some limitations also. And these limitations may be optimal use of energy sources. So here is the term optimal, which is of importance. We will discuss about it. Then there may be some control issues, right? Which control is the most effective one, which is the most easier one, etc. Then definitely there are some lack of system protection in microgrids, especially in DC microgrid production, right? And regulatory standards, they are still in the this process of development in some countries, and some countries are still not having any policy about this microgrid implementation in their own countries. And final question is, that is of the customer's privacy. There are still some issues with some customers that they are not ready to reveal their personal data of energy consumption or electricity consumption with the controllers or the operators, right? Because they say it is going to affect their privacy when and in which day or at what time they are using what loads. Yes, they do not want to reveal that, what type of loads they are using, when they are using it, when they are using the TV, when they are using some other loads. So they are not ready to participate in these microgrid programs, because when a centralized controller is there, so definitely it is going to fetch the information about the load consumption, about the available resources, about the predicted load in future time on the basis of the previous data. So for this, they are not ready. Now, I told you earlier how to define that any power system may be qualified as a microgrid. So I have taken this very old example, very first commercial historical event, which is available in the history, that in 1882, Thomas Edison's first commercial sale of electricity in that Pearl Street, that was having a length of 11 miles, right? Some specific number of customers were there. Some specific number of loads were there, means capacity is defined, geographical boundary is defined, electrical conduction boundary, you can say, that is defined, generation is defined, everything is defined, right? So can this be classified as microgrid? Yes. If you tick every condition of microgrid definition, this particular experiment or this particular event of commercial sale of electricity, this is a successful microgrid which qualifies all the requirements of microgrid. So now we can say that at that time, what Thomas Alva Edison was selling electricity, that was through a microgrid in some specific boundary of geographical location. So such 50 microgrids were installed by Edison and his company at different locations, you can see, right? But what happened? After some time, it was observed that if we are generating electricity in mass or in large, with large generation capacity, it is going to be more economical. What is that? Economies of scale, right? So through this economies of scale, this trend was shifted towards large centralized power plants, right? And what happened? Right now, we are having the thermal power plants of the capacity 500 into 4 megawatts, means 2000 megawatt thermal power plant is situated at some particular location, right? As per the load requirement, definitely, or as per the resources availability. These are the two basic conditions on which these such plants are established. And then what happened? When this centralized power plants became the trend, then they needed this transmission connections, right? Because their location was either very close to the load center or very close to the resource available, that is the coal, right? So that transmission was required, and definitely later this was converted into monopolistic utility, and it made the power system diagram a vertical diagram: generation, transmission, and distribution, and then consumption. Means it was a simple monopolistic situation. And in those situations, those microgrids of earlier years, they simply faded out because they became the old, out of fashion. Then recently, these technologies are driven just because of reliability is the major concern of some power systems in some countries. Good power quality is a concern nowadays. In last 2-3 decades, the power quality problems, they have become the main concern. Then after that, this reliability also became a main concern. And right now, we do not find those situations when the electricity is acceptable if it is not having a good power quality. Or most of the places, even in our country, where the power situation was not that good in, you can say, just 20 years back, it was not that good, as we are a witness of that. But right now, the situation of electricity is improved a lot, right? So in this situation, when this is having a feeling of fulfillment of electrical load, then definitely we are in a condition to talk about the better reliability and better power quality of the power system. And third is the electricity consumers, who we are at this receiving end, right? They have become more knowledgeable, and they prefer to be more engaged in certain questions of reliability, power quality, better power regulation, etc., etc. So these are the few reasons which are making microgrids popular nowadays. Now, here comes a point from where this term microgrid came into existence. Who is the first person who developed this term and how this concept came into existence? So the history is very interesting in that there was a researcher named Robert Lasseter. I have seen his paper since till this last 1918. There was some paper by Robert Lasseter that I have seen, and they are in the area of this microgrid only. So this 1990, he was a researcher at University of Wisconsin-Madison. And there were several buildings, there were which were the part of that university campus, right? And they all were installed with some micro turbines up to the capacity of maximum 100 kilowatts. And they were being used, these microturbines were used as backup generators of each and individual buildings, right? And what was the problem? Lassater wanted to control them from a single control, right? And the motivation of research was to operate them synchronously as one integrated power generation source. And those turbines, they were not made in that way. They were not developed in that way, right? They were developed only for the individual operation of each and every device, right? So they were not ready to cooperate with each other. What was the result? There was power failure. That was the result. Dangerous voltage was the part of the power system when they were running simultaneously, and frequency fluctuations were there, which led to the crash of the setup. Means everything failed. Finally, he kept on working on that, and he developed a hardware, and that hardware he referred as controller, right? And the purpose of controller were to regulate the voltage and frequencies in a way that multiple generators and load installed at different buildings in that university campus, they operated in a connected way seamlessly to form a power grid. And this was the birth of the term microgrid. This particular setup is still available in Columbus, Ohio. I have got some details about this particular thing in this paper of 2018 of Vaidyanathan. There are research papers also available from Robert Lassater. What he has done, he has published his own findings in some IEEE meetings or in conferences. In first talk with the titles Microgrid was read by Lassater. It was given by Lassater in 2002 IEEE PES winter meeting. And he explained that microgrid should be able to operate independently, that we call islanded mode or grid connected mode, but shall be successfully capable to operate in both the modes. Second is the system should be modular, so that the new generation sources and loads can be added. Means it can be extended in a modular way. It can be reduced in a modular way. Simple thing. Third is microgrids could be linked to the central grid. Yes, it means it shall be capable to operate in a grid connected mode. It shall be capable of drawing or supplying power as per the situation from or to the larger system, that is the grid in this case. And this particular paper was published, or you can do different occasions. One was 2002 PES general meeting, and second was the event. Second event was the PESC 2004 happened in Germany. So this was the initial year when this Lassater published his concept, his findings, and after that there was a beginning of foundational research on microgrid. So this foundational research on microgrid was started as two different projects in United States of America and Europe. The first protocol, or you can say the first initiative, was Consortium for Electric Reliability Technology and Solutions, that is CERTS, and that is still a viable protocol for the microgrid operations as per the United States industrial and academic requirements for the research and development regarding the microgrid. Second, which was the project Microgrids, that was started in Europe, and the second part of this project was started with the name More Microgrids after the completion of this particular project, right? So these are the two foundational research in two different parts of the globe towards the objective of microgrid CERT project. There is a specific website of this project, that is certs.lbl.gov. That is a United States government website. So this particular CERT project was initiated in 1999. The collaboration, the founding members were Lawrence Berkeley National Laboratory, Oak Ridge National Laboratory, Pacific Northwest National Laboratory, Sandia National Laboratories, the PSCRC, and Electric Power Group, right? And the purpose was to research, develop, and disseminate new methods, tools, and technologies to protect and to enhance what? That is reliability and efficiency. Reliability of power system and efficiency of the competitive electricity market, which was just in the beginning stage at that time. So this is a very basic and most successful protocol or project which was started in United States of America. If you want to read more, you may visit that website. This is capable to give you sufficient details about this, right? Or you can read this paper of 2002 also, which is author is P.N. Overholt, a IEEE publication of PES Society summer meeting. So what happened? This particular CERTS project, it started a thinking or working towards the microgrid concept, right? And it said that as per its vision, that microgrid can incorporate multiple distributed generation sources or DERs, right? And still it can present itself to the existing grid, either as a typical customer who is ready to take the power from the grid, or it may supply power to the grid as a very small generator as per its available capacity, right? So it is very clear from here that it is connected at a point of common coupling to the distribution system through a switch, where is the basic control, which this switch position can decide the mode of operation, either grid connected or islanded, right? And it definitely, the purpose was, in case of its available local resources, it can fulfill the requirement of the loads, and if it is not capable, those DERs are not capable to fulfill the requirement due to some certain constraints, then it can take supply and overcome those challenges of the DERs. But these particular CERT protocol or CERT project that emphasized on which points? Number one, seamless and automatic switching, so that reliability is improved. Reliability was the major motivation for this CERT project. Better reliability of the American power system. Number two, the passive control strategies were highlighted, such as reactive power versus voltage, active power versus frequency, flow versus frequency, so that different issues of the power quality, different issues of voltage regulation or some other frequency regulation, they can be addressed in a better way. And definitely if these are properly addressed, so what is going to happen? The reliability is going to increase. It means most of the outages, region of the outages, they are addressed. So definitely better reliability is the outcome. Third is, that is the third point, that is the most important point, is the primary motivation of the CERT was to improve reliability. It was nowhere concerned with those greenhouse gas emissions. It was not the concern at all, right? But there was a provision, yes, in the CERT protocol, microgrids can incorporate the renewable energy resources which may contribute towards the decrease in GHG gases or greenhouse gases. So definitely, this was not the inclusion of this RERs was not the main motivation. It was a side motivation, or you can say, or by allowing this participation of RERs. But this particular microgrid project, which is having a website as www.microgrids.eu, right? This particular European Union project was having the similar technical challenges like management, islanding, better islanding, safe islanding, control strategies for both the modes, protection equipments, communication protocols, right? But this was a huge project, as the number of stakeholders were a large number, 5 to 6 in that case of CERTs. In this particular case, there were 22 participants from 11 European Union countries. They were industries, they were academia, and so many commercial organizations also. Means if you see it here, you can find that University of Manchester from Britain and some other universities from different countries, they were the part of it. And some companies like ABB, some other big names of European market, they were the stakeholder in that. And in this way, total 22 participants were there who were the part of this microgrid project. If you try to compare these objectives of these two different microgrid projects, which are the foundational research in those areas, and typically they may be referred as the present protocols in these countries, they have a very clear comparison. Means reliability of power supply was the motivation of this CERT protocol. Reduction of environmental impact, that was the motivation of this European microgrid project. Reduction of investment in plant, equipment, and cost, and that was the motivation towards the improved efficiency of the market. That was the American motivation. Increase of energy efficiency, yes, it was a part of both these protocols. Ensure diversity of energy supply was not clearly mentioned in any of these, but yes, both of them were allowing these distributed generations, renewable resources, as they were allowing them for participation. Power supply to island or remote site, yes, that was the in favor of this European project microgrid, and this ride-through capability provided by energy storage for better reliability, yes, it was the motivation or objective of both these microgrids projects, either this CERTs or microgrids of European Union. So this is the two different approaches of foundational research, you can say, in area of microgrid. And it all started in very early years of 1999 and 2002. You can, this is the history of the microgrid. Now, a classification of microgrid is available in this 2018 paper, and we have discussed a lot in the past about the classification of the distributed generation, right? And here we are talking about the microgrid classification. They may be classified as power type, AC or DC. There is a third type, that is hybrid, also in discussion nowadays. Then comes the supervisory control. You may take it as a centralized, decentralized, and some other modes of control are also available in literature right now. Then comes the operation mode. Yes, they are right from the beginning. One is islanded and second is grid connected. Number of phases, yes, single phase, three phase, etc., etc. And on the basis of application, they are residential, commercial, industrial, utility, municipality, military, etc., etc. There are some specific papers where you can find the global installment or installation of microgrids for specific purposes with capacity. We will also have a list. We will discuss that list in our later slides about this application or purpose of microgrid as per their installation. So if we say that a microgrid is, if we talk about microgrid architecture, so we have talked a lot, composition of microgrids, modes of microgrids, purpose of microgrids, etc., etc. We have discussed them in detail. So if we talk about the control objectives consist, yes, active and reactive power control, that must be independent. Correction of voltage profile, power quality issues, fulfillment of microgrids, load dynamic requirements. Agreed. So proper operation, MGs require proper control strategies for micro source and load controllers, microgrid system central controllers, MGCC, and distribution management system, that is also a part of this. We will discuss in detail about these control objectives and energy management system in later slides. So if we summarize this as core functions of MG control, there are three functions sections: upstream network interface, microgrid control, and protection and local control. Means on both the sides of the microgrid, there shall be proper protection and control for the successful operation of the microgrid. So this microgrid control system can be classified on the basis of control architecture. There are three types of control architecture: centralized, decentralized, and distributed or multi-agent. If we talk about control methods, they are with communication and without communication. The control in terms of control mode, they are classified as master-slave mode, peer-to-peer mode, combined mode, as per the available literature. I'm giving this classification, and I have taken the help of this particular paper of Electrical Energy Systems published in 2021 for developing this classification. This diagram I have taken from there, this I have taken from different literature. Then comes the control level. This control level talks about this primary, secondary, and tertiary. So this is all about, this particular diagram covers each and every aspect of the microgrid control, possibly. There may be some new researches also, but up to this point of time, it covers a lot and so many control systems and their types. So this particular diagram, this clearly explains all those things which we have discussed in the last slides. So what it says that this is a microgrid central controller, and these are the different stakeholders, you can say, of the microgrid system. This dark line in black color, this shows the energy flow, and this dotted yellow line, this represents the information and communication flow. And what may be the components, different components or stakeholders of the microgrid, you can say that there may be a main grid which may allow to operate this microgrid in a grid connected or islanded mode using this switch. Second stakeholder may be electric vehicles, which are also referred as battery on wheels, right? Which have the capability of working in V2G, V2H, etc., etc. Different operating modes are there. Then comes smart buildings, which have the capability of, sometimes some smart buildings also work as a microgrid. In other scenarios, there are smart buildings who are capable of taking the load, fulfilling their load requirements as per the economic values means when the electricity is the cheapest, or some other parameters may be set as per their intelligence or control of their intelligence. Similarly, there are smart homes. There are some other types of energy storage systems. They are also the part or component of it. There may be some conventional generator systems like this diesel generators or micro turbines, etc., etc. And there may be some renewable energy resources. It may be rooftop solar. It may be a wind turbine in the backyard, or maybe some community-based setup, means producing large capacities, not the distributed one. So in that case, there is a centralized controller, which we are calling microgrid central controller or MGCC. Clear? And every component or every stakeholder is connected to the central controller through its local controller LC. Right? So here you can easily justify what is the role of LC. Means LC control is limited to their each and every stakeholder or component, and central controller is responsible for the complete operation or complete parametric assessment and delivery of the performance of the complete microgrid. And everyone is capable of supplying the load. Here in this case, there may be some flow of electricity in two directions. There may be some flow of electricity in only one direction. Clear? And depending upon this data, which is communicated through these local controllers or these information network, this particular microgrid central controller may also take data from outside, and those parameters may be weather forecast, which is going to decide the future power consumption or future power generation from these renewable energy sources in the coming time. And accordingly, it may share some information or it may do business from the energy market by the assessment of its generation and consumption both. Either it shall purchase electricity from the energy market to fulfill its requirement, or it shall sell its surplus electricity available at some instant in future, and accordingly it may make some agreement in advance, right? So this is a complete microgrid architecture. And of course, I think this particular diagram is capable of explaining what is smart in it and how these microgrids can be the component of the smart grid architecture of future, right? So let me make you very clear that smart grid is not going to be a very new type of power system like you change your old car and bring your new one. No, a smart grid is definitely going to be a system, your existing system, with some better control and better capabilities of control, with some new automation system, with some new sensors, with some new controls on this existing power system, right? And definitely, if you see with this perspective, so this microgrid is definitely going to be a building block of this smart grid system of future. As I told you that there are three different types of control available for microgrid. Here you can see that different centralized control, decentralized control, and distributed control, they are available, right? And here you can see that this MGCC is having a centralized role with these local controllers, as I discussed in the last slide also. This decentralized controller, there is no communication among these decentralized controllers, right? And they are responsible for controlling their own components. There is no MGCC, there is no interconnection, right? So this is the decentralized one. Third is the distributed control. In this case, there is a communication between these distributed controllers, but there is again no MGCC. Clear? So in this way, these are the different control techniques which you can compare, and you can compare on the basis of different matrices of the control, and these matrices may be responding speed, control accuracy, economic performance, computational complexity, communication burden, stability to single point of failure, and scalability, right? And if you compare them one by one, and on the basis of that diagram which I have explained you in this last slide, you may say that responding speed is definitely going to be the low in the first one, where MGCC is processing everything, right? Where MGCC and interconnection between different controllers is missing, that is having a very high speed, and the distributed is having the medium one. It is clear from the diagram. Second is control accuracy, definitely, which is slowly processing the information. It is going to give you a better control. With MGCC, it is going to be a comparatively better control than the decentralized one in case of distributed. That's why it is said medium high, and in case of decentralized, it is low. Of course, the economic performance is low in case of decentralized, but it is medium and medium high in case of distributed. Computational complexity is very high in this case of centralized, and the low in case of this decentralized and distributed. Then comes the communication burden, high in case of centralized, low and medium high in these two cases. Decentralized second one and third one in this particular diagram as I shown. Then stability to single point of failure, all is connected. So it is low in this case, high in this case, and medium in this case. Then comes the scalability. Scalability is high in this case, sorry, high in this case. You can simply add on more modules, right? And every module will take care of its own control, right? So here it is high. But scalability is comparatively lower in this case of distributed control, where it has to establish a link with other distributed controllers, and it has to establish a link or share the information with centralized control. In those cases, this scalability is medium in comparison to decentralized, for which it is high. In recent cases, there is a literature survey you can find. If you make a survey of recent techniques, you will find that there are some hybrid control approaches also, where they are taking the advantages of the better points of each one among these, and they are making some hybrid choices of these controls to achieve better in a better way for a better control. 3 control layers in a hierarchical structure. They are having primary control, secondary control, and tertiary control, and there are different goals. We will move fast as we are not taking control as a primary objective of this particular lecture. I have simply introduced you the control, and here you can find out that this primary, secondary, and tertiary control, what are the different methods and what are the functionalities, right? So primary control is in the range of milliseconds response time, and this tertiary control, it moves towards the minutes, as it is given specifically in this particular slide, at 0 to 1 second, 0 to 10 second, and tertiary control in terms of minutes. Here you can find that the functionalities which come under this primary control, they are active and reactive power sharing, group control, local coordination and protection, MPPT control, etc. Then for secondary control, it has this voltage frequency deviation correction, real-time load management, protection and fault restoration. It means it is at the level of network at and as well as microgrid and its interconnection. This primary control was only at the level of within the microgrid. Then this tertiary control, which needs a response times in terms of minutes and mostly in terms of 5 to 10 minutes, that is optimal energy management, economic dispatch and unit commitment, and energy market interaction. It means the time layer is going to be more than 10 minutes also. So different signals are interacting with each other at different control levels. And in this way, this is a interconnection of microgrid and main grid also using this control switch. So there are different comparison of microgrid supervisory control. We have discussed a lot. We will move ahead. A summary of this AI and machine learning techniques that can be implemented in microgrid control. They may be of different types: supervised, semi-supervised, unsupervised, and reinforcement also. In case of supervised, this is again classified as classification and regression. If you want to read more about this AI/ML techniques for microgrid control, you may refer this paper of 2022, which is in Energy and AI. And its title is Implementation of Artificial Intelligence Techniques in Microgrid Control Environment, Current Progress and Future Scopes. This deals in detail about the AI or machine learning control techniques for microgrid control. That particular paper also refers this diagram of control techniques or control strategies about the microgrid. And definitely this classifies into these 4 categories: centralized, decentralized, distributed, and hierarchical. And accordingly, it gives control for different actions as or different components, as I have told you in the previous diagram also. And simply those particular jobs or roles of the microgrid components have been detailed here with some specific AI technique which are used in different literature, or they may be used in future, that has been described. Same paper of 2022. Then comes microgrid energy management system. So this energy management system is definitely a software and hardware combination, you may say, which provides the better control and this optimal sharing of the energy resources. There are several methods for energy management, and these are functions of microgrid energy management systems are: they may monitoring, analyzing, and forecasting of power generation of DERs, load consumption, energy market prices, ancillary market prices, and meteorological factors, right? And in case of microgrid energy management system, they may take this data from renewable resources, means different components are here, including this weather forecast also. And this particular data monitoring analytics is done for forecasting purposes. And this forecasting may be helpful in microgrid's participation in energy market, in ancillary market, using the real-time control. Clear? So these are the functions of the microgrid energy management system. If we define or want to discuss the energy management strategies in detail, so definitely all the literature which deals with energy management strategies, they are simply the optimization problems which have certain specific objectives and constraints, right? So this green blocks, they represent the objectives, and these are the constraints which are to be taken care in solving these objective functions as a optimization problem. So what may be the objectives? The objectives may be listed in general as operational and maintenance cost of conventional generators, levelized cost of renewable resources, operational and maintenance cost of energy storage systems, greenhouse gas emission cost, load shedding penalty cost, losses happening, they are the losses and they are having a cost. Then demand response incentives. If someone is participating in demand response program, then that particular customer is liable to have some advantages or rewards from the utility companies. So that may also be objective. Then outage and interruption cost, because they happen at some time just because of some technical and non-technical reasons, they may take place. Then of course, the energy storage devices, the example is battery, and that is its cost is degrading day by day with the uses, and finally comes the energy transaction cost, right? So there are some limited objectives which we have tried or attempted by some different researchers to list down. Similarly, the constraints may be physical limit of energy storage, physical limits of conventional generators, reliability, reactive power support, demand response, output limits of renewable resources, energy balancing, and network constraints. They are in general, they are giving you a list of objectives in green and constraints in red in this particular diagram. And if you wish to categorize these objective functions in different categories of cost optimization, battery lifetime optimization, battery capacity optimization, emission optimization, so you may categorize those objective functions given in green in the last diagram. They may be categorized like this. In case of cost optimization, you may consider the operation and installation cost, cost of battery energy system degradation, startup and shutdown cost, cost of electricity. Battery capacity optimization may be taken as capacity of renewables, power conversion capacity, battery storage capacity. Emission optimizations may be taken for a specific component of the that particular gas emission, and including this emission cost. And then battery lifetime optimization is also an important thing, because battery is going to be a sizable part of the cost when we are talking of it as an alternative source of electricity in some moving vehicle, either, or in the case of microgrid. So that is definitely going to be a very high cost. And definitely this particular cost or operating cost or degradation cost of battery is going to depend on state of charge, depth of discharge, and number of cycles. This is all clear if we definitely, of course, we are aware with the chemistry of the battery, and these are the things which are clearly connected with those basic concepts. And if you want to classify those constraints in red also in the last diagram, they may be classified in these 5 categories, such as charging and discharging constraints, energy balance constraints, system reliability constraint. Excuse me. Then capacity constraints and environmental constraints. So this is a complete set of classification for different references, different objective functions and constraints, which may be a part of or which may be a component of this energy management optimization problem. And this energy management, if we talk about, so there are 2 different directions, right? So this microgrid management aspect, directions may be taken as energy management and control. We have talked a lot about the different objectives and constraints of this energy aspect, right? So this is all optimization problem. It may be a multifunction objective function or single function objective function, right? And they may be solved as a global convergence for this optimization thing. Second, this microgrid management control we have discussed a lot about, and this may be in these aspect directions. And if we explore the available literature, you will find that this energy management has been investigated more than the control aspects, right? So there is more literature on the energy management optimization things in comparison to control, and this may be a motivation for you to explore more in the control aspect if you are interested in future research in that particular area. Or you may further explore this optimization things also. There are always new findings which are being useful. Then comes a concept of this multi-microgrid systems. Definitely, this is the architecture which uses the communication, this interconnection of microgrids, as I told you earlier. And definitely, if you explore the control of this MMG structure, multi-microgrid system, so it is also having this primary, secondary, and tertiary control similar to the individual gate, other than, and this all is being monitored by a operator at large. This particular magazine article of 2014 of IEEE Power Energy magazine, here you can find that there is a successful implementation of microgrid in Illinois Institute of Technology, and this is a microgrid in MB distribution network, right? And this is established at IIT Microgrid, and the major contributor for motivator for this system was M. Shahidepur, right? And with this, the author said they have published this particular article in this energy magazine, PES magazine, that is only connect microgrids for distribution system restoration. So definitely they are talking about the motivation taken from the deferral of the new cost, right? By implementing this microgrid, they have deferred the investment on generation, new transmission, and distribution network by implementing this microgrid at Illinois Institute of Technology, right? So this particular microgrid at Illinois Institute of Technology is represented here in diagram, right? And this particular medium voltage microgrid is having its microgrid functions here. They are represented at in this diagram, and the control task associated with each function, right? So here you can find out there is a primary control, there is a secondary control, and there is a tertiary control. As it is similar to the previous tables we have discussed, that primary is at microgrid level, secondary is between this between the layer of this primary and tertiary, and this is having this between microgrid and grid. So if we are talking specifically about this particular example of successful example of Illinois Institute of Technology microgrid, it is having a coupling switch at point of common coupling, which is making the control. It is collecting data from using these meters and PMUs. It is having building controllers in different buildings of the institute. It is having HRDS switches, battery storage, wind turbines, solar PV, gas turbines as distributed generation sources of electricity at different locations within the campus, right? And this is primary controlled by this primary controller, and it is having this set point information from the secondary control, and using these set point information, it is making control of here, right? And this primary, these components, they are directly connected with this grid coordination also. And this secondary control, this is having economic demand response, means optimal selection of the source, right? By using which source at what time will be a cost-effective solution of energy provisions, that is being selected here. And this particular islanding and the synchronization control is also here using this emergency demand response. And it is also having a self-healing capability of reconnecting, of disconnection of the affected part before it is converting to a blackout for the complete system or damage to the complete system. And after removal of that fault, it may be that particular part of the network may be reconnected also. So this all capabilities it is addressing, and this there is a short-term reliability algorithm is also applied at the microgrid master controller, which is consider this seamless islanding using this particular switch and resynchronization and applying this emergency demand response and this self-healing, all available in this particular block in the case of major outage on either side of this point of common coupling. So this economic operation addresses the this economic operation addresses the optimal generation scheduling of these DG units in grid connected and islanded modes both. Also, this economic operation applies economic demand response to minimize the cost, as I told you earlier. And functionally, a 3-level hierarchical control is applied in this particular grid operation. In the second diagram here, you can find out that this is a master controller, which is connected to this building control system, distribution control system, right? For this particular microgrid, the primary control is based on the droop characteristics of DER units for sharing the microgrid load. Secondary control perform corrective actions to mitigate this secondary control performs corrective actions to mitigate frequency and this voltage errors, you can say, which are being introduced by the droop control. And this tertiary control manages the power flow between the microgrid and the utility grid, right? And provides the optimal scheduling of DER units for in both the modes, that is islanded and grid connected. Tertiary control also provides ancillary services to the utility grid by participation and earning some revenue for this thing, such as voltage and frequency regulation and restoration services by its participation with the main grid, this grid coordination, you can see. So this primary control is performed at the DER level using the local component information. With this, each information is being information from each component is shared with the primary control, and this master controller performs the central. This master controller here, this performs the centralized secondary and tertiary controls here, and this is having generation control system, gas turbine generation, solar PV wind, and storage control, charging station, battery storage, etc., etc. So this hierarchical control structure of this Illinois Institute of Technology microgrid is in front of you. If you have any question, you can ask, or for more details, you may refer this magazine article. Here, master controller obtains the campus generation through its different observation units such as meters and PMUs. And load data, it also generates using SCADA and other measurement things. This microgrid is equipped with building meters, and as it is shown here, this is meters, and it is having some 12. It is having around 12 PMUs for measurements that together report the building electricity consumptions and instantaneous values of DER data, DER units data to the master controller, which is here. Clear? And this master controller, this determines the optimal hourly solution at base case and contingencies, and sends this tertiary control signals towards those generating units. Rather, you can say those DG units, means on-site generation storage, and this HRDS switch this HRDS switch is high, you can say it as HRDS switch. This switch, particular HRDS switch is here, and this is called high reliability distribution system switches, right? And definitely the next is it is connected directly with these building controllers. So this all happens in a real time. All these controls, they are integrated, and these building controllers, they facilitate energy management by reducing or shifting the different loads at different locations according to the different specified modes by the control or by the main operator of the system. So in this way, it is clearly visible from here that it may operate in both the modes, that is islanded as well as distributed, right? So in case of island mode, there is a provision of natural gas turbine and battery storage system that maintains the rated frequency and the voltage through the primary and secondary control functions, because it is this tertiary control is not available at that stage, and so on, right? So this is all about it. I invite you to read this particular article that is around some 10-11 pages. You may find it useful, or if you find it more interesting, you may read some further works of this author, especially Mr. Professor Asheesh, if you are more interested in the control of microgrids. So finally, as I promised you that we will talk about the drivers, barriers, policies, constraints, etc., in the last. So we are in the last phase of our lecture. We will definitely talk about the drivers and barriers. So if we talk about the drivers, there are three different categories, right? One is energy security. Second is economic benefit. Third is clean energy integration. And you can find out that this is directly connected with those primary definitions, or those different, sorry, not with the definition, they are directly connected with those foundational research programs named CERTs and microgrids, where these particular drivers are clearly identified in their objectives, right? So if we talk about the energy security, means better reliability or more reliability of the power system in case of some country specific objectives. So there is a data available in one paper of 2018 that is related to microgrid paper, and I think the first author is Hirsch. I think I have mentioned it somewhere in my there is a paper by Hirsch. I think it definitely it is there in somewhere, right? So this particular paper says that in US, this particular duration of 2003 to 2012, there was a grid outage cost of $18 billion to $33 billion per year. That is the average cost, right? And what are the reasons for which this cost is calculated? That may be lost output and wages, spoiled inventory, delayed production, and damage to the grid. These were the conditions which were the result of the severe weather only, right? And you just estimate the cost. Clear? So this severe weather is basically affecting more to the long transmission lines or distribution system. And if distributed generation based microgrids are there at local locations, so definitely these damages may be reduced. Clear? Second is cascading outages, right? What happened in case of in year 2003 August, month of August, right? There is a historical blackout of USA Northeast blackout, where 50 million people were affected and around 62,000 or megawatt or 62 gigawatt of load was affected, right? This more details are available in this 2005 transaction, ITB transaction on power systems.
Excuse me, sir.
जी
Sir, excuse me, sir.
जी बोलिए.
Sir, there is specified up to 9:30, sir. So,
Yes, I will complete in some next 5 minutes.
So there is still 5 minutes. So just I am requesting you, sir, please compile so that they can ask some question.
I will.
Thank you, sir.
So these I will just simply modify. I will not go in detail. So these are the basic drivers: energy security, economic benefits, and clean energy integration, right? And then economic benefits of infrastructure cost saving also means by deferral cost of heavy investments. And this Brooklyn microgrid is a very successful example. There are several articles in IEEE magazines, and this IEEE magazine, what we call monthly magazine, you can find some article related to this Brooklyn model of microgrid, and there you can study how they have this investment has been deferred, huge investment has been deferred. The fuel saving is also there if you are reducing this transmission and distribution losses. So these losses, and definitely, as I told you, that there are several opportunities to participate in ancillary services of the utilities. They are not present right now in our country, but I hope in next 2-3 years such services may be available for participation. So these are the economic benefits which are the drivers. Then, of course, the clean energy initiatives where these renewable energy resources participation is going to the part, going to give this reduction in greenhouse gases. So that is also a major driver for this microgrid participation. So this is all. And as we can see that there are some examples of these successful examples of this microgrids. There are some example in India also, where this L&T Chennai campus is having a microgrid in India with a capacity of 1820 kilowatt. This Santa Rita's jail, if you give in detail, I can give you, this is a CERT specified microgrid with some 1.2 megawatt rooftop solar, 1 megawatt fuel cell, 5 numbers of 2.3 kilowatt wind turbines, 2 numbers of 1.2 megawatt emergency backup DG set, diesel generators, advanced energy storage system of 2 megawatt hour, 12 kilowatt subcycle disconnected switch of landing capability, etc., with energy import export capacity, means control provisions are there, biotronic interfaces are there, right? So this is a very successful example, Santa Rita jail, which is away from the land within some island, right? So this is a successful example, which is working very successfully since several decades. And still some future trends in microcontrol may be multi-microgrid operation, soft switches applications, meta-heuristic optimization-based control, and load management. They may be future trends where you can involve yourself in some future research in the area of microgrid. Challenges, there are some legal and regulatory challenges. Still, there are uncertainty because these are the political, there may be some political issues also, there may be some social restrictions also. They are the challenges. Then comes the interconnection policy with the utility. In some countries, it is still not developed. That may be a challenge. Then utility regulation and utility opposition also, because the cost of electricity is rising day by day. You can see in some countries that this is going to be simply unaffordable, right? So utilities are also opposing the unwarranted participations of distributed generations or microgrid, which was earlier not the scenario, but as the economic margins are reducing day by day, then this opposition from the utility is also coming. And definitely it has a future prospects. This microgrid is a component, a smart component of a smart grid. So definitely its participation will enhance the adaptability and acceptability of the smart grid infrastructure, which is the future of the energy system scenario. And definitely the market structure, degree of market decentralization, peer-to-peer sharing, blockchain, these are the few technologies which are definitely going to support the safety, security, and other issues in the market perspective. So definitely there are so many things to come, right? So there is a long way still to go towards the objectives of microgrid, which is still being treated as a subset of the smart grid paradigm. So we have traveled a lot, but still more ways to go and achieve the target, right? So I have attempted to discuss so many things, so many aspects about as a basic introduction, key challenges, components, etc., etc. So this is all from my side. And if you have any questions, I welcome you for the questions, please. And if you feel that I have taken a lot of time and I have not given you sufficient time, as Dr. Shivam may say that, so you may take my email ID. I am always ready to reply your queries. My email ID is asheesh@mnnit.ac.in, ASHEESH, and definitely this is double N also in MNNIT, right? So do not make it single N, otherwise it will reach to NIT Jaipur, right? So this is the email, you may write me, and definitely I promise you to reply in next 24 hours about some queries, right? I'm ready, always ready to for better collaborations in this directions. I also work in the area of electric mobility, which is also an extended aspect of, you may take it as a microgrid aspect, right? Where we do some work on this V2G and G2V capabilities integration in the network. So you are always welcome for collaboration. Please.
Thank you, sir. Thank you so much, sir.
You have, I promised you, I have not taken the break in between, right?
Really, sir. This is appreciable. Appreciable point, sir, because continuously 2.5 an hour you have spoken. So this is a very wonderful things, and you have also covered.
I have also tested myself that this was not tested since post-COVID. So thank you for giving me this opportunity to test myself also. Thank you.
Thank you. So from audience side, if you have any query, you can ask or you may ask on sir email ID. Already it is showing. So sir will already announce this. He will reply.
Let at least one question come here, so that I may also be confident that we two are not the only persons who are awake here. Any questions, please?
Audience side, you may ask any question.
I think it is too late.
Good evening, sir. Dr. Garima Goswami here.
Namaskar.
Right? Yeah, namaskar, sir. I'm continuously listening you, and this is definitely a very informative lecture.
Yeah, I know that most of them are here and they are listening.
Yeah. Yes, sir. Yes, sir. Definitely. I have a very small kid of 1 year, but still, I just cast the time to listen you, and it was really very informative lecture. As I wanted to know one thing, sir. What are the challenges regarding power quality or harmonic generations in this microgrid? So is there any particular like active power filter or passive filter design so that we can reduce these harmonics or to enhance the power quality?
Yeah, thank you. So yes, I can reply your question that as you are aware that wherever is the converter, right?
Yes, sir.
Or any power electronic device like SMPS, or it all depends on the loads also at the interface of supply side also. So there are the harmonic issues or the power quality issues, right?
Yeah.
So
yes,
depending upon the capacity or capability, there are the specific power quality suppressant also. You may say that they are capable of improving the waveform, which waveform deformation is the outcome of those power quality reasons, and some power wave quality improvement is made by those active power filters or some other power electronic interfaces, right? So there are no specific things. There are certain standards also, but such as harmonics, they are being governed by that simple 519. Voltage sags, there are specific or some voltage unbalance, there are some specific standards. So they are the specific solutions as per the standards, and there are certain acceptability range is also increased nowadays, right?
Yes, sir. Yes, sir.
I hope I have answered your question.
Yeah. Thank you so much, sir. But I just searched out that the active power filters are right now including in transmission system, not in distribution system yet. Yeah, on the distribution side.
Is it vice versa? Active power filters, basically they are limited to that, they are having some limited capacity, right?
Yes,
so
yes.
They are more applicable for this distribution system. Is it?
Yes, sir. Yeah, yes, sir.
G. Okay, if you have any further question, you may write, ma'am.
Sure, sir. Sure.
A learning experience to learn something new from your queries.
Yeah, yes. I have your mail ID, so yeah. I wish to be in contact with you in future also.
Sure, ma'am. It will be my pleasure.
Thank you so much, sir.
Thank you, ma'am. You have asked a good question. And any other question from audience side? So, okay, sir. I want to ask one point, sir. You have given light on AMI, artificial intelligence, yes, machine learning for microgrid. So right now they are working, many researchers are working on this area, sir. Is it not, sir? So there is still a scope for actually this is a new area.
That's why I have included and highlighted that particular paper also of 2022, right? That is a recent paper of Elsewhere publication, right? You may explore that thing and that paper, and definitely the AI and ML, they are the new trend nowadays. Everyone wants to use those things.
Yes, yes.
You all know that they are the data specific approaches. So definitely how to implement them and how much data of past and previous record may be utilized for that, and how to utilize that, that may be a question on the performance of those things.
Yes, yes, sir. So thank you, sir, from my side also, sir.
Thank you. Thank you.
Yes, sir. You have accepted invitation, sir, for that. Very, very thank you, sir.
Always, Shivam sir. REC Kurukshetra or MNNIT Kurukshetra is my alma mater.
Yes,
and
yes.
It has a very important role in my position, and I'm always available.
Thank you, sir. Thank you so much.
Please keep on calling.
Thank you, all participants who have attended very sincerely. So thanks for them.
Thank you,
sir. Thank you, all of them. Thank you, sir.
Namaskar.
Namaste, sir.
Namaskar.